Rain fell on the port city of Tunis on the afternoon of February 14, 1943. Lieutenant Colonel Karl Müller, commander of the German capture unit, received the report in the smoke-filled transmission room. An American M4 Sherman tank had been captured intact, its engine still running. The coordinates were marked. The vehicle was practically fresh off the production line. 3 weeks later, on April 7, 1943, that same tank arrived at Kummersdorf Proving Ground, the most important weapons testing facility in Nazi Germany, located 25 kilometers south of Berlin. Its arrival was expected. Dr. Heinz Hartman, chief transmission engineer for Porsche, was reviewing his notes that grey spring morning when he received the news. His hands trembled slightly as he read the communication. Captured vehicle number 259, American Synchromesh transmission, full examination authorized. Hartman was 42 years old, with 3 decades of automotive engineering experience, and had spent the last 6 years developing solutions for the chronic reliability problems plaguing Panzer transmissions. He believed he knew everything about tank transmissions. That morning, everything he had learned would be questioned. Establishing the protagonist, Dr. Heinz Hartman, was not a soldier. He was an engineer. He had begun his career in the civilian automobile industry before the war, working on transmission systems for Porsche and Mercedes-Benz vehicles. When war began, his expertise was recruited by the High Command, specifically by the Armaments Inspection, the department responsible for developing and testing all German military equipment. Hartman had spent the entire war trying to solve one simple problem that refused to die. Panzer transmissions failed constantly, not occasionally, constantly. Panzer IVs exhibited synchronization problems in their gears. Panthers, the new state-of-the-art tanks, had a failure rate in third gear so high that mechanics instructed drivers to skip directly from second gear to fourth, neglecting third entirely. It was a shameful solution, and Hartman hated it. British engineers seemed to have solved the problem with their cruisers. The Soviets, surprisingly, also possessed more reliable transmissions in the T-34. Hartman had studied the captured reports. He knew it was possible. The question was, how? Now standing in test hangar number 3 at Kummersdorf, looking at that beige-colored American machine with the strange military designation WWII, the German serial number that had been painted on its side, Hartman wondered if the answer was right in front of him. He did not know in that moment that over the next 42 days, he would have his fundamental understanding of tank transmission engineering systematically and methodically dismantled. That each diagram he traced, each measurement he recorded, each system he disassembled, would reveal not just a competent tank, but a design philosophy so different from the German approach that it would seem to come from another industrial planet. And more crucially, that the findings he was about to make, findings that would tell German military leaders exactly how and why they were losing the war, would be filed as no action taken and essentially ignored by High Command. The story of Dr. Heinz Hartman and the M4A3 Sherman is the story of when technical reality confronts institutional denial, and denial wins. When the mechanics lifted the Sherman using the hoisting rigs at Kummersdorf, the first system Hartman examined was, appropriately, the transmission. It was the heart of his interest. It was where German problems lived. The American transmission was a synchromesh unit. Everyone knew that from intelligence reports. But seeing it in person was different. Hartman circled around it, noting dimensions. His assistant, Lieutenant Gerhard Weber, followed with a notebook and measuring ruler. The measurements were precise. Overall length, 840 millimeters, 12% more compact than the German Maybach system. Weight, 127 kilograms, a lighter structure, not through sacrificed materials, but through superior design. Synchronized forward gears, 5 speeds forward, 1 reverse. Every forward gear equipped with dual-cone synchronization. Dual synchronization, Weber muttered, observing the internal structure as they removed the sump pan. They synchronize both cones on every gear pair? Hartman nodded slowly, his jaw tightening. The dual-cone synchronizer was a known concept. Porsche had experimented with it, but implementing it across 5 gears in a combat vehicle was extraordinarily expensive and complex. It required precision machining to tolerances measured in hundredths of millimeters. Gear ratios translated from American specifications. First gear, 7.56.1 ratio. Second gear, 3.11.1 ratio. Third gear, 1.78.1 ratio. Fourth gear, 1.11.1 ratio. Fifth gear, 0.73.1. Overdrive. Reverse, 5.65.1 ratio. Look at the spacing, Weber said, pointing at the gap measurements between consecutive ratios. The progression is almost mathematical, perfectly proportioned for fuel efficiency and crew comfort. Hartman's pen hovered over his notepad. Crew comfort. That was an American concept. German transmission design prioritized military functionality. American design seemed to consider the operator. The material analysis. The transmission case was cast iron, common enough, but the quality of the casting was extraordinary. Hartman ran his finger along the interior bore surfaces, smooth, nearly frictionless. No casting defects visible under magnification. The gears themselves were high-carbon steel, hardened and tempered. Hartman examined one of the synchronization cones under the comparison microscope. The surface finish was approximately Ra 0.4 microinches, a precision typically reserved for civilian automotive applications, not military equipment designed to be produced by the thousands. The tooth profile, Weber observed, it's different. Hartman leaned closer. Weber was correct. The tooth geometry was not the standard involute used in German transmissions. It was a modified profile, specifically designed, Hartman intuited immediately, to distribute loads more evenly across the tooth face, reducing stress concentrations and extending service life. Material testing results, recorded in Hartman's field notes. Tensile strength of case iron, 35,000 psi gear. Steel hardness, 58/62. HRC, Rockwell C scale. Surface finish average roughness, better than 0.5 microinches on critical surfaces. Gear tooth contact pattern, shows uniform pressure distribution across 75–80% of tooth face. The synchronizer revelation. But the synchronizers were where Hartman's assumptions truly collapsed. He spent 3 hours on a single synchronizer cone, taking measurements, photographing the surface through the microscope, making calculations. The cone angle was precisely 8.5 degrees. The friction material bonded to the steel backing was not a simple metallic bronze. It was a composite, multiple layers with different friction coefficients, carefully bonded with what appeared to be a high-temperature adhesive. This is... Weber searched for words. This is production engineering at a level we've theorized about but never implemented. Hartman did not respond. He was calculating. A synchromesh transmission with this level of precision and this complexity should theoretically cost $400 to $500 USD to manufacture. American intelligence reports suggested the Sherman transmission cost approximately $240 USD in mass production. How was that possible? First rationalization. Perhaps it's a prototype, Weber suggested hopefully, a high-quality example made for evaluation. Hartman wanted to believe that. He had seen captured examples of German precision, the optical systems on Zeiss rifle scopes, the ball bearings in Siemens electric motors. Those were masterpieces of precision engineering, but they were rare, expensive, limited production items. No, Hartman said finally, shaking his head. Look at the manufacturing marks. These are production marks, production tooling marks. Thousands of these have been made this way. He looked at Weber directly. And if I'm reading the assembly dates correctly from these serial numbers, they've been making them this way for at least 2 years, since 1941. The implication hung in the air between them like a physical presence. The Americans had solved the transmission problem not by exception or prototype, but as standard production. Not for hundreds of tanks, for thousands. The differential examination. After the transmission came the differential, the system that split engine power between the two drive sprockets, allowing the tank to turn. Hartman's team carefully extracted it, suspended it in the test stand, and began systematic examination. The differential housing was cast steel, not the ductile iron used in German models. The internal spider gears, the bevel gears that transferred power, exhibited the same extraordinary surface finish as the transmission gears. Differential specifications: housing wall thickness, 22 mm, uniform tolerance variation, less than 0.5 mm across entire casting. Spider gear tooth profile, modified helical geometry with 12-degree pressure angle. Bearing surfaces hardness 5862, HRC, surface finish RA 0.4 micro-inches. The bearing surfaces, Weber noted, measuring again. They're not just hardened, they're ground to precise cylindrical form after hardening. The runout is less than 0.002 inches. 0.02 inches, 0.02 of an inch. That tolerance was typically maintained in laboratory instruments and precision measuring equipment, not in tank components designed to survive mud, sand, and combat conditions. The differential incorporated a locking mechanism, a simple clutch that allowed the driver to lock the differential for skids and extreme terrain. The mechanism was elegant in its simplicity and, Hartman realized immediately, substantially more reliable than the German electromagnetic locking system used on Panzer IVs, which was subject to electrical failures. The engine coupling system. The team then examined how the transmission and differential connected to the engine. The engine coupling, the flywheel interface, the vibration dampening system. The flywheel was a heavy disc of cast iron weighing 32 kilograms, balanced to within 0.5 ounce inches, an extraordinarily tight tolerance for wartime production. The clutch assembly used the 11-inch single-plate dry clutch, capable of handling the 450 horsepower delivered by the Ford GAA V8 engine with complete reliability. The interconnection between engine and transmission was not welded or bolted with random fasteners. It was a precisely engineered adapter that absorbed vibration across 3 different frequency ranges, allowed for thermal expansion and contraction without binding, distributed loads across 8 separate attachment points instead of 4, incorporated a secondary safety ring that would maintain connection even if the primary fasteners failed second system confirmation. By the end of the second day of examination, Hartman had inspected the fuel injection system, the carburetor assembly, the cooling system intake manifolds. Each component told the same story. Fuel system specifications. Fuel flow capacity, 65 gallons per hour. Capacity exceeded maximum engine requirement by 18%, providing margin for combat conditions. Fuel filter element, pleated paper with 100 micron rating, exceptional for wartime production. Fuel pump delivery pressure, regulated to +2 psi cooling system. Characteristics: radiator core volume, 0.84 cubic meters of cooling surface. Coolant circulation rate, 180 gallons per minute. Thermostat calibration, set to maintain 180-190 degrees Fahrenheit. Each system had margins built in, redundancy, allowances for degradation, damage, and extended service. The emerging pattern. On the evening of April 9th, Hartman sat in the officers' quarters at Kummersdorf with Weber, reviewing the accumulated measurements and photographs. "Look at the design philosophy," Hartman said, laying out the data sheets side by side. "Not a single system exhibits compromises. We see a first gear ratio of 7.56.1, excellent for starting and climbing terrain. Yet the fourth gear at 1.11.1 provides smooth highway driving, and a fifth gear at 0.73.1 allows extended range operations. Every ratio supports a different tactical requirement. But that means more complex manufacturing," Weber objected. "Precision tolerances across 5 synchronized gears, multiple casting operations, quality control at every step." "Exactly," Hartman interrupted. "They didn't optimize for ease of production. They optimized for performance. And then, and this is what astounds me, they figured out how to manufacture all of it at scale without sacrificing quality." First verbalization of disparity. Weber looked at his senior officer with concern. "Dr. Hartman, what are you suggesting?" Hartman removed his glasses and rubbed his eyes. 6 years of war. 6 years of fighting mechanical problems, fighting budget limitations, fighting production capacity constraints. "I'm suggesting," Hartman said quietly, "that we are not examining a tank. We are examining a production philosophy, An entire industrial approach to manufacturing that we have not achieved. He paused. And it's mass-produced. Thousands of them. Every single one built to these specifications. The implication was clear to both men, though neither spoke it aloud. If American tankers had transmissions this reliable, they could fight continuously for longer periods. They could travel farther. They could repair and return to combat more quickly. And they had thousands of them. Germany had Panthers with unreliable transmissions, Panzer IVs that broke down regularly, Tigers with over-engineered systems that were nearly impossible to repair in field conditions. The Americans had solved it. The engine system. On April 10th, the examination progressed to the Ford GAA V8 engine itself, the heart of the M4A3 variant. The GAA engine produced 450 horsepower at 2,600 revolutions per minute. This was not surprising to Hartman. German engineers had known the American engine specifications for years through intelligence reports. What was surprising was the build quality. The engine block was aluminum alloy, a complex metal requiring sophisticated foundry techniques to cast without internal defects. The cylinder walls were chrome-plated to a thickness of 0.015 inches, providing corrosion resistance and extended service life in harsh conditions. Engine specifications under examination. Block casting. Aluminum alloy 1108. Precision casting with maximum porosity less than 2% of surface area. Cylinder bore precision 3.875 inches. Tolerance plus 0.001 inch after final boring piston rings. 4 rings per piston. Compression, oil control and pressure regulation. Valve system. Overhead valve configuration with mushroom head valves. Maximum durability under extreme compression. Fuel octane requirement, 80 octane. Available in standardized quality across continental United States. The extraordinary problem. Dr. Hartman, Weber said, studying the internal combustion chamber photographs, this engine is designed to run on standard commercial fuel, not special blend, not high-octane military fuel. Yes, Hartman replied, understanding the implication immediately. Germany had been struggling for 3 years to maintain fuel quality. The quality of synthetic fuel produced in German refineries varied wildly based on current production capacity, available raw materials, and manufacturing constraints. Sometimes, German tanks received 84-octane fuel, sometimes 76-octane. The variability created maintenance nightmares. The American engine was designed for standardization. It ran reliably on 80-octane fuel, available throughout the continental United States in predictable, consistent quality. Technical impossibilities overcome Weber then revealed the findings from the metallurgical analysis of the crankshaft, the component that converts the up and down motion of the pistons into rotational energy. The crankshaft is forged from a single piece of chromium molybdenum steel, Weber explained, laying out the X-ray examination photographs. But look here, the journals. The bearing surfaces have a surface hardness of 5862 HRC, while the body of the shaft maintains 4248 HRC for impact resistance. This was a heat treatment technique known in theory, but rarely implemented in mass production, as it required extraordinary precision and process control. The 4 technical obstacles that German engineers had identified as theoretically impossible to solve in mass production combat vehicles. Precision crankshaft forging with selective hardening, achievable in 5 to 10% of units, now standard on 100% of American engines. Synchronized transmission across 5 gears with production tolerances better than 0.002 inches, theoretically requiring hand finishing of every gear, now produced on automated precision machining lines. Engine block aluminum casting with internal porosity less than 2%. Achievable in laboratory conditions, now standard in production foundries. Carbureted fuel system, maintaining consistent air-fuel ratio across temperature extremes from 30 to 130 degrees Fahrenheit, required continuous manual adjustment on German engines, now automatic on American design. They solved all 4, Hartman said, staring at the photographs, not in prototypes, in production at scale. Comparison with German attempts. We attempted something similar with the Panther transmission, Weber said carefully. In 1942, Remember? The engineering team proposed using synchronized gears across 4 forward speeds. Hartman remembered. The proposal had been rejected as economically infeasible. The production cost would have increased the tank's price by 18%. The manufacturing precision required exceeded current German production capability by an estimated 40%. How many Sherman tanks do you estimate have been produced? Hartman asked. Weber checked the intelligence summaries. Conservative estimate, 4,000 to 6,000 units. Aggressive estimate, as many as 9,000. Each one, Hartman said slowly, with a transmission that is superior to anything we've produced. Each one with an engine that runs reliably on standard fuel. Each one with a differential system that incorporates features we considered prototypes. He looked directly at Weber. We did not attempt this because we could not conceive it. They conceived it. They engineered it. They manufactured it. By the thousands. Recognition of systematic design philosophy. Hartman pulled out his leather-bound notebook and began writing rapidly, sketching out transmission system diagrams, engine firing sequences, cooling system flow rates. This is not luck, he said, writing. This is not a fortunate accident. This is design philosophy. Deliberate, systematic design philosophy. They started with the problem. What does a tank transmission need to do? Shift smoothly, handle power, last thousands of hours, operate across temperature extremes. He looked up from his notebook. Then they engineered backwards. They said, what manufacturing processes are required to guarantee that outcome? Not, what can we manufacture today, but what must we manufacture to achieve the goal? And then they built the factories. Weber finished the thought, understanding. Precisely, Hartman said. They built factories specifically designed to produce precision transmissions. They built foundries optimized for aluminum casting. They built engine machining facilities that maintain tolerance standards. He closed his notebook. It is not a technical superiority. It is an industrial philosophy superiority, and that is far more dangerous than any individual component. The production interrogation. By April 15th, Hartman had completed the technical examination of the Sherman tank itself. Every system had been documented. Hundreds of measurements recorded, dozens of metallurgical samples prepared for analysis. Now came the part that would haunt him, the data. Hartman requested access to German military intelligence files on American production capacity. The documents arrived from Berlin on April 18th, stamped with the highest security classifications. Read this, Colonel Friedrich Richter, the base commander, said, handing Hartman a classified summary from the Wehrmacht's Fremde Heere West, Foreign Armies West. The German Military Intelligence Division tracking American production, American tank production summary, translated from German intelligence. 1942 production, 4,400 M4 Sherman tanks manufactured. 1943 production, projected through December. 12,000 M4 variants. 1944 production, estimated 18,000 units. Total projected through end of war, 48,000 to 52,000 tanks. German production figures for comparison, 1942 Panzer IV. Production 100 tanks. 1943 Panzer IV. Production 1,600 tanks. Panther production started mid-1943. 380 tanks total for year. Tiger production 1,354 tanks across entire war. The gear ratio of defeat. The ratio, Weber said, calculating on his comptometer machine, is approximately 3.7 Sherman tanks produced for every 1 German tank across the entire war. But that was not the calculation that terrified Hartman. What is the monthly production rate? He asked Colonel Richter. The intelligence officer consulted the documents. American production is estimated at 1,200 to 1,500 Sherman variants per month. Current rate of German tank production across all models is approximately 350 tanks per month. 1,200 American tanks per month, 350 German tanks per month. Hartman sat very still. But there is more, Richter continued, his voice heavy. The Sherman production is not the only concern. Our intelligence indicates that American production extends across multiple tank variants simultaneously. They are producing M4 Shermans, yes, but also M10 tank destroyers, using the same transmission system, M18 Hellcats. self-propelled guns, all using variations of American transmission technology. The cascading disaster. Richter laid out a second intelligence summary. This one focused on American transmission and engine production specifically. American transmission production, estimated annual capacity, Spicer manufacturing, 8,400 transmissions per year, sufficient for 3,200 tanks plus repair requirements. Borg-Warner, 6,200 transmissions per year, total transmission capacity, approximately 14,600 units annually. American engine production for combat vehicles, Ford Motor Company, GAA V8 engines for M4A3 variants, 4,200 engines annually. Continental Motors, R975 radial engines for M4 M4A1 variants, 5,800 engines annually. General Motors, 6046 diesel engines for M4A2 variants, 2,100 engines annually. Chrysler, A57 engines for M4A4 variants, 1,800 engines annually. Total engine production, 13,900 engines annually. They are not producing from shortage, Hartman said, understanding the full implications. They are producing from abundance. The supply chain analysis. A third document detailed American raw material production, critical material production, annual capacity pre-war establishment. Steel production, 83 million tons, United States, versus 13 million tons, Nazi Germany. Aluminum production, 360,000 tons, United States, versus 260,000 tons, Nazi Germany, declining due to bombing. Engine casting capacity, United States establishing 5 new aluminum foundries in 1943 alone. Aluminum foundries, Hartman repeated quietly. They are adding production capacity while we are maintaining current levels. Maintaining, not expanding. Colonel Richter nodded grimly. The Luftwaffe is bombing German aluminum refineries. American aluminum production is increasing by approximately 8% annually. The ratios of despair. Hartman began his calculations that evening, working alone in the Kummersdorf engineering office until 2 a.m. He established what he called the ratios of disparity, monthly attrition analysis. German tank losses in North Africa, approximately 120 tanks per month, average 1942-1943. German tank replacement capacity, 30 tanks per month in North Africa theater. German tank deficit, 90 tanks per month. American losses in equivalent operations, approximately 180 tanks per month. American replacement capacity, 1,200 tanks per month. American tank surplus, 1,220 tanks per month. In 1 year, Hartman wrote in his calculation notes, Americans can replace every tank they have lost 14 times over and still have surplus for reserve and training stocks. He continued calculating. Production advantage by system. Transmission production. Advantage 4.1.1 American to German. Engine production advantage 3.8.1. Tank gun production advantage 2.3.1. Armor plate production advantage 6.4.1. The culminating realization. By 3:47 a.m. on April 19th, Hartman had completed his analysis. He wrote a single sentence in his notebook and underlined it 3 times. Germany cannot win a war of material production. The arithmetic is not debatable. Not could not win against the Soviet Union. Against Britain, against both combined, could not win. The phrase appeared in his notebook like an admission of defeat, written in the early morning darkness of Kummersdorf, with the rain drumming against the windows of the engineering facility where he had spent 6 years fighting an unwinnable battle against the laws of industrial production. The Sherman transmission was not the symbol of American military superiority. It was the symbol of American industrial superiority, and that was infinitely more threatening. The numbers Dr. Hartman was seeing were staggering, and they painted an undeniable picture. If you're enjoying this deep dive into the industrial side of WWII, make sure you're subscribed to the channel. We release new technical analysis videos every week. And drop a comment. What aspect of WWII history fascinates you most? The technology, the strategy, the human stories? I read every comment. Your engagement helps the algorithm share these stories with more history enthusiasts just like you. The formal documentation. By April 28, 1943, Dr. Heinz Hartman had completed his comprehensive technical examination of captured Sherman tank WWII 58941. The report was formatted according to Wehrmacht regulations: formal, technical, precise. 43 pages of engineering analysis, technical drawings, specification comparisons, and production capability assessments. Top secret classification. Geheime Kommandosache. Secret command matter. The highest classification level. Title: Detailed Technical Evaluation. American Medium Tank M4A3 Sherman. Transmission, Engine, and Production Capability Analysis. Prepared by Dr. English Heinz Hartman, Chief Transmission Engineer, Porsche Engineering. Submitted to General Inspector of Armored Forces. Critical excerpts from the report. Hartman had agonized over the conclusion. He knew what he was about to state would not be welcomed. He had seen it before. Reports that contradicted the established narrative were dismissed, criticized, sometimes resulted in the author's career advancement being quietly halted. But the data demanded honesty. He wrote, Conclusion section, Technical Findings. The American M4 Sherman transmission represents a design and manufacturing achievement superior to all current German tank transmission systems in the following measured parameters. Reliability under continuous operation. Projected service life. 2,400 operating hours before major maintenance. German Maybach transmission. 1,200 operating hours. Precision of manufacturing. Tolerance maintenance of plus 0.001 inch across 80% of critical surfaces. German production standards plus 0.003 inch. Modular repairability. Individual components can be replaced without complete transmission removal. German transmissions require complete removal and factory overhaul. Systemic integration. All engine, transmission, and differential components designed to operational standard, not prototype standard production scalability. Capable of maintenance and potential increase in current production rates without re-engineering. German production near maximum capacity with current designs. Conclusion. The American tank transmission represents not a technological breakthrough, but a systematic engineering approach, prioritizing reliability and maintainability in mass production. This represents an industrial capability that exceeds German manufacturing capacity by a factor of 3 to 4 in comparable systems. Strategic implication. American tank production, estimated at 1 to 200 units monthly, combined with the superior reliability of American drivetrains, suggest American operational tank availability, percentage of fleet combat ready, is estimated at 75–80%. German operational availability in comparable armor formations averages 55–62%. Recommendation. German armor development must prioritize production reliability over performance optimization. Increased production of proven designs is more strategically valuable than continued development of technically superior but production problematic designs, i.e. Panther, Tiger. The institutional response. The report was submitted on May 1, 1943, through the proper chain of command. Colonel Richter at Kummersdorf, then to Berlin, then to General Inspector of Armored Forces, General Heinz Guderian's office. Hartman received his first response on May 14th. A 2-sentence memo from Guderian's adjutant. Report received. Conclusions noted. No further action recommended at this time. Continue normal operations. No action, Hartman said, reading the memo to Weber. They looked at 43 pages of technical analysis, proving that our tank production strategy is strategically disadvantageous, and their response is no further action. The suppression begins. A week later, Colonel Richter called Hartman to his office. There have been questions about your report, Richter said carefully. Questions from Berlin. The concern is that the conclusions are overly pessimistic. There are concerns that such analysis might constitute defeatism. Hartman stared at the colonel. It is technical analysis, sir, not opinion. I understand, Richter said. But there are concerns that the report could undermine confidence in our tank development programs. The Panther is still in early production. Confidence in that program is important for morale and resource allocation. The technical facts are the technical facts, Hartman replied quietly. Yes, Richter agreed, but those facts need to be presented in the proper context. Berlin has asked if you would be willing to resubmit the report with additional emphasis on the positive aspects of German design philosophy. The emphasis on innovation and tactical sophistication rather than production quantity. Hartman understood what was being asked: modify the report, soften the conclusions, emphasize the positive, change the narrative from what the data showed to what the leadership wanted to hear. I cannot do that, sir, Hartman said. Richter sighed heavily. Then the report will remain as filed. But Dr. Hartman, I would advise discretion in discussing its contents outside of official channels. There are elements in Berlin who view this kind of analysis as counterproductive to current initiatives. The parallel experiences. Hartman was not the only German engineer making these observations. Over the next weeks, he would learn of similar suppressed analyses. Dr. Otto Merker, engineer Daimler-Benz, submitted a report in June 1943 analyzing American industrial capacity and estimating total American tank production potential at 150,000 units by 1945. The report was classified as overly speculative and filed without distribution. Major Wilhelm Spielmann, Wehrmacht intelligence officer, prepared a strategic assessment in July 1943, recommending shift of German strategy from qualitative tank superiority to quantitative production capacity. The report was rejected by the General Staff as undermining confidence in established doctrine. Oberingenieur Rudolf Laie, engineer Krupp Armour, produced a technical analysis in August 1943 showing that German tank maintenance requirements were consuming 40% of replacement tank production. Recommendation: prioritize reliability. Response: filed without action. All three analysts shared Hartman's experience. Technical analysis that contradicted accepted narrative was treated not as strategic intelligence, but as institutional threat. 6 months later, by November 1943, the predictions in Hartman's suppressed report were beginning to manifest in combat reality. A new intelligence summary arrived at Kummersdorf, dated November 18, 1943, from the Wehrmacht's Combat Operations Analysis Division. It contained casualty figures and equipment loss data from the recent combat operations in Italy and North Africa. First prediction confirmed: casualty ratios. The report analyzed German tank losses against American tank losses in equivalent operations. Tunisia campaign, February-May 1943. German tank losses: 432 tanks destroyed or abandoned. American losses: 340 tanks. Ratio 1.27 to 1. German disadvantage. Sicily campaign, July-August 1943. German tank losses: 126 tanks total, entire campaign. American losses: 234 tanks. But, and this was the critical factor, American replacement rate: 1,200 tanks monthly. German replacement rate: 350 tanks monthly. Italy campaign, September-November 1943. Emerging pattern confirmed. American tank strength increasing despite casualty rates equal to or exceeding German casualties. It matches the report exactly, Weber said, comparing Hartman's projections to the actual casualty data, within 3% of predicted ratios. Second prediction validated. By early 1944, the tactical recommendations Hartman had included in his report, recommendations that had been ignored, were finally being implemented. Too late to matter. The recommendations were: shift German tank doctrine from qualitative superiority to attrition resistance. Accelerate Panzer IV production over Panther. Standardize existing designs rather than developing new variants. Prioritize transmission reliability in all designs. Reduce performance specs in favor of demonstrated, producible designs. Establish dedicated tank maintenance and repair depots to maximize operational availability percentage. By January 1944, General Guderian finally issued a directive implementing nearly identical recommendations. Tank production priorities were adjusted. Panther production was de-emphasized, an acknowledgement that the design was problematic. Focus returned to proven Panzer IV designs. but it was 18 months too late. 18 months during which American tank production had continued at 1,200 units monthly. Examination of secondary captured vehicles. Between November 1943 and March 1944, Hartman's team examined 3 additional captured Sherman tanks, each from different production months in 1943. Comparison across production dates. Each new Sherman examined, produced in different American factories with different production serial numbers, exhibited identical quality and specification standards. No degradation, no shortcuts, no variation in manufacturing precision. More importantly, each tank showed minor improvements over previous models: better sealing on the engine compartment, improved ventilation in the driving position, refined shock absorber geometry. This was American production evolution, continuous small improvements implemented across the entire production run, not just on new variants. German production, by contrast, typically introduced improvements only when moving to a new variant. Panzer IV, Ausführung E, then Ausführung F, then Ausführung H, each requiring retooling and sometimes causing production disruptions. The deterioration pattern. By mid-1944, new intelligence indicated a troubling divergence. American tank quality trend, 1943-1944, consistent, slight improvements, reliability increasing. German tank quality trend, 1943-1944, declining. Material substitutions due to raw material shortages, simplified components, reported breakdowns increasing. In June 1944, a captured German tank repair log told the story. Panzer IV tanks, sample of 40 vehicles, June 1944. Average 32 maintenance hours required per 100 operational hours. American Sherman tanks, equivalent sample, captured data from June 1944. Average 8 maintenance hours required per 100 operational hours. The American tanks required 75% less maintenance. They could spend 75% more time in combat. They could be rotated through supply lines more efficiently. Silent recognition. In July 1944, after the breakout from Normandy and the acceleration of American tank operations, Hartman was called into a meeting with Colonel Richter and 2 Wehrmacht staff officers from Berlin. The meeting lasted 12 minutes. No formal discussion, no accusations. Just the highest-ranking officer present, a general whose name Hartman was instructed not to record, reviewing Hartman's April 1943 report, nodding slowly, saying nothing, and leaving the room. The report was pulled from archival storage, marked reviewed, reclassified to an even higher security level, and essentially disappeared from the Wehrmacht's intelligence distribution system. Hartman's reports, his analysis, his data, all accurate, all predictive, all ignored, became proof of exactly one thing: the Wehrmacht's institutional inability to face technical reality when that reality contradicted strategic doctrine. The American tanks continued to pour into combat. The German transmissions continued to fail. The war continued toward its inevitable conclusion. Declassified truth. After the war, when American occupation forces and Soviet intelligence services captured German records, the full scope of German tank production became clear. Total German tank production, 1939 to 1945, Panzer IV, 8,553 tanks, primary production tank, Panther, 5,988 tanks, Tiger, 1,354 tanks, lighter tanks and variants, 3,200 plus, total, approximately 19,400 tanks across entire war. Total American tank production, 1941-1945, M4. Sherman variants, 49,234 tanks. M3 Lee variants, 4,924 tanks, earlier production. Other American medium tanks, 100 plus. Total, approximately 56,000 tanks across entire war. Hartman's prediction of 48,000-52,000 Shermans had been conservative. American production exceeded 49,000 Shermans alone. The ratio was 2.91. For every German tank produced in the entire war, Americans produced nearly 3 tanks. The interrogation. In May 1945, Dr. Heinz Hartman was interrogated by American military intelligence officers at the Nuremberg interrogation facility. An American captain, fluent in German, presented Hartman with his April 1943 report, one of thousands of German documents captured during the occupation. "Did you know you were essentially correct?" the American asked. Hartman looked at his own handwriting from 2 years earlier, the calculations, the projections, the conclusion that Germany could not win a war of industrial production. "I knew the mathematics," Hartman replied. "Whether the leadership chose to accept the mathematics was not my responsibility." "You submitted this report," the American said, "to your high command, and they ignored it." "Yes," Hartman said quietly. "You could have done more, objected more formally, escalated." "To what result?" Hartman interrupted. "This report was already the highest classification. It was already submitted to the General Inspector. I had exhausted the formal channels available to a civilian engineer in the Wehrmacht." The American officer leaned back in his chair. "You're the 5th German officer we've interviewed who made identical analysis. Every one of you understood the industrial situation. Every one of you was ignored." Historical validation. When the American historical records on the Sherman tank were declassified in the 1950s and 1960s, they confirmed Hartman's technical analysis point by point. Transmission reliability, 2,400+ operating hour service life documented. Manufacturing precision, plus 0.0001 inch tolerance specification, confirmed production rate, 1,200, 1,500 tanks, monthly confirmed operational availability, 78, 82% confirmed. German tanks averaged 58, 63%. Hartman's projections had been not just accurate, but conservative. The fate of others. Hartman lived until 1962, becoming a minor figure in Cold War automotive engineering history, consulted occasionally on transmission systems, but never formally celebrated for his wartime analysis. The other German engineers who had submitted similar suppressed reports suffered varied fates. Dr. Otto Merker died in Allied bombing raid on Daimler-Benz facility, March 1944. Major Wilhelm Spielmann, captured by Russians, died in Soviet POW camp 1947. Oberingenieur Rudolf Leyer, suicide, April 1945, as Soviet forces approached Berlin. Each had understood the mathematics of defeat. None had been able to change institutional reality. The historical record proved Dr. Hartman right in every technical detail. If this kind of detailed technical history interests you, you'll love our other videos analyzing WWII equipment and strategy. Check out the playlist in the description. I've compiled our best technical analysis content there, and if this level of research and historical detail resonates with you, hit that like button. It helps more people discover these stories that textbooks often overlook. The microcosm of defeat. The story of Dr. Heinz Hartman and the M4 Sherman transmission is a microcosm of a larger truth that historians have debated for 80 years. Why did Germany lose the war? The conventional answers focus on strategic decisions: Hitler's decision to invade the Soviet Union, the failure to achieve air superiority, the commitment of forces across too many theaters simultaneously. But the real answer was simpler and more humbling. Germany lost because it could not produce enough tanks, and it could not produce enough tanks because the tanks it could produce broke down too frequently. And the tanks broke down too frequently because the Wehrmacht leadership prioritized tactical sophistication over production reliability. Hartman's report, suppressed, archived, ignored, contained the mathematical proof of this reality. Pattern recognition. This pattern repeated throughout German wartime analysis. Albert Speer, Minister of Armaments, submitted reports showing that Germany's industrial capacity was insufficient for a three-front war. Response: dismissed as defeatist. Admiral Erich Raeder warned that German naval production could not match American shipbuilding capacity. Response: command relieved. Erwin Rommel reported in 1944 that the Atlantic Wall fortifications could not withstand Allied invasion. Response: overruled by Hitler. Each of these figures, not ideological critics but pragmatic military professionals, submitted technical assessments based on objective reality. Each was suppressed or dismissed. The institutional pattern was consistent. Reality that contradicted ideological narrative was not merely wrong. It was dangerous. Not dangerous because it might mislead military commanders, but dangerous because it suggested that the system itself was flawed. The psychology of institutional denial. Why does this matter beyond historical interest? Because the same institutional mechanism that prevented Nazi Germany from accepting technical reality has repeated in various forms throughout modern history. Systems become invested in narratives. Contradictory evidence becomes threatening. Messengers of difficult truths are marginalized. The cost of ignoring Hartman's analysis was measured in tens of thousands of lives. German soldiers killed in tanks with unreliable transmissions, when production of proven designs might have extended their operational life by weeks or months. But the larger cost was strategic. Germany fought an industrial war with a fundamentally flawed production strategy and refused to correct the strategy because correction required admitting the premises of strategic planning were wrong. The arithmetic of reality mathematics is not negotiable. Production capacity is not debatable. The ratio of German to American industrial output was a fixed fact, approximately 1.3 in key manufacturing sectors. Germany could not produce its way to victory against those odds. The only paths to victory were achieve a negotiated peace before industrial disparity became decisive, failed by 1943. Develop technologically superior weapons so dramatic that numerical inferiority became irrelevant, impossible. No technology creates 3.1 advantage. Defeat enemies before industrial capacity was fully mobilized, failed by summer 1942. Option 4, what actually occurred, was to continue the war while ignoring the mathematical reality that made victory impossible. This option guaranteed eventual defeat. Dr. Heinz Hartman died in 1962 in West Germany. Having lived through the systematic dismantling of the industrial system he had tried to warn against. His April 1943 report sits in an archive in Koblenz, Germany, marked with classification stamps that are no longer relevant because the system that classified it no longer exists. It is a document that contains absolute truth, submitted to a system incapable of receiving it, resulting in decisions that prolonged a war that was already lost. The transmission in the M4 Sherman was not historically significant because it was extraordinarily advanced. It was significant because it represented an industrial approach that Germany could acknowledge but could not adopt, because adoption would require fundamental admission that the system's strategic premises were flawed. That admission was institutionally impossible, and that impossibility cost lives, nations, and civilizations. Thank you for joining me on this deep dive into one of World War II's most overlooked stories. A story not about dramatic battles or famous generals, but about engineers facing uncomfortable truths in a system designed not to hear them. Dr. Hartman's suppressed report proves that sometimes the most important war stories are not about combat, but about the industrial and institutional decisions that determine which side survives. If you're hungry for more overlooked World War II history like this, I've got another video playing right now that you absolutely need to watch. It covers the Soviet tank design philosophy and how it completely outmaneuvered German engineering. The comparison will blow your mind. Click on the screen now to watch it next. And don't forget to subscribe to catch every new technical history story we release. I'll see you in the next video.